Hello AP Physics students, this is Dr. Berenzi and this is lesson 8.3, and in this lesson we're going to be learning about something called Kepler's laws of planetary motion, and then we're going to be able to apply those laws to determine the motion of planets. So let's go ahead and get started here. Actually, I want to start with a little history. Why are these called Kepler's laws of planetary motion? And it's all due to a couple of people that are big names in how much we know about planetary motion. And the first one is the guy on the left. His name was Tycho Brahe. He was a Danish astronomer who lived in the late 16th century. And his role in all of this is that he was a very good observer of the locations of planets. He actually went to the King of Denmark and asked if the king would fund an observatory where he could very carefully and meticulously plot the position of planets as they go across the sky. And Brahe was extremely meticulous about this and took some very, very good data. And without his contribution, the guy on the right, Johannes Kepler, who was a German mathematician, would have never been able to come along and come up with his laws of planetary motion without Brahe's very careful observation. So it's really due to the two of them put together. Brahe did the observations, and then Johannes Kepler, who was a mathematician, actually was able to figure out some mathematical patterns to the observations that Brahe made. So when Kepler took Brahe's observations, he recognized that there were three laws of motion that the planets obey. And by this time, this had been after a guy named Nikolai Copernicus came along and proposed that the solar system was actually had the sun in the center, which is what we call a heliocentric model, as opposed to a geocentric where the Earth is in the middle of the solar system and everything goes around it. So these two guys recognized Copernicus's work, and because they were Protestants, they didn't have as much as Copernicus had to deal with as far as the Roman Catholic Church and all of that history. So these guys are relatively free to take what Copernicus thought and run with it. So, Kepler came up with three laws of planetary motion, and he figured out that first of all, and this was probably one of the most brilliant of the three laws of motion here, is that what Kepler recognized is that each planet actually travels not in a circular motion, but in an ellipse, and that was kind of like that was a big deal for his time. Because not only is the sun not exactly at the center, it's actually off to one side, which really threw some people for a loop at the time. So what is an ellipse? You guys probably probably didn't get enough exposure to what are called conical sections when you were taking pre-calc, but an ellipse you can make actually on a piece of paper by taking two thumbtacks and tacking them into, into a table or something like that. And then you have a string. It's a loop of string actually, and then you tighten the string so that your pencil is at one point, and then it goes around these two thumbtacks. And then what you can do is you can trace your pencil and keep that loop of string stretched, and the shape that you'll make when you go all the way around is what's called an ellipse. And the thumbtacks are at what are called the foci, which is plural of focus. So there are two foci to every ellipse, and the sun, Kepler recognized, has to be at one of those two foci. which was a really amazing observation on his part. And even though we draw these as ellipses and they look like they're very oblong, actually the orbit of each of the sun's planets is nearly circular. Not quite circular, and Kepler was able to discern that thanks to Brahe's data, but it's very nearly circular. For example, the Earth's distance to the sun only varies by about 1.5% of its average value. So this is actually it's basically an ellipse that looks very much like a circle. Let's put it that way. So that's Kepler's first law of planetary motion. Then another thing that Kepler realized or recognized is that you could take a line from the sun to the planet, and then as the planet goes through its orbit, that line will sweep out a certain amount of area. So as the planet goes from here over to here, that line that connects them will sweep out this much area. And if you take a similar change in time sometime later on in the planet's orbit, it will sweep out a different area. But what Kepler recognized is that the area of both of these swept out areas is equal. And it's kind of like a less awkward thing, but it says two things. First of all, it says that the closer a planet is to the sun, so this is the sun right here, the closer a planet is, the faster it moves. So here in its orbit, it will go very fast, and it will have to sweep out it'll have to go farther in its orbit because it has to sweep out the same amount of area as if it were over here. It doesn't go as far in the same amount of time, but that's because this distance is so much farther to the planet. So the planet experiences its fastest motion when it's closest to the sun, and its slowest motion when it's farthest away. And what we're going to find out actually in the next lesson is that this is actually a consequence of a law that we are actually more familiar with. But Kepler wasn't familiar with it, so he had to come up with this language about sweeping out equal area in equal time. It's not something that we really use on a practical basis, but it tells us you're closer to the planet, you're going faster. Or excuse me, you're closer to the sun, you're going faster. You're farther away from the sun, you're going slower. Alright, then he came up with a third law of planetary motion, which actually is something that we use quite a bit and that we're going to get a lot of practice with, and that's this. If you have two planets and they are in orbit around the same star or the same planet, then you can say that the square of the period of the planets is proportional to the cube of what's called the Semimajor Axis. Okay. What is, first of all, the period? Well, hopefully you recognize that the period is the amount of time it takes to complete one orbit. So the amount of time it takes to go all the way around would be this period in time. And then what's the Semimajor Axis, what that is that is half of the long axis of an ellipse. So if I draw an ellipse on here, and I don't want to actually interfere with that actual one right there, then if I draw a line across the long length right here, that is what's called the major axis. So going all the way across is what's called this major axis. And then if you want the semi-major axis, you take half of it. So you cut it in half. So we could cut it in half. And we could, let's go ahead and erase this part. Oops. Well, alright, there we go. So this distance right here would be called the semi-major axis right here. Okay. Let's see if I can get that in there. There we go. So that is what's called the semi-major axis, and this is what R would be. Now, for all intents and purposes, when you go to actually look up in your table of astronomical data, you're not going to actually be given the semi-major axis. What you're given instead is what's called the average orbital radius. And I think on the table it just says orbital radius, but it implies the average because the planet goes around in an ellipse, so it changes distance from the sun as it goes through one complete orbit. But this semi-major axis is actually that orbital radius that is reported in the table. So if you're freaking out because you can't find semi-major axis, well, it's actually the same as orbital radius, average orbital radius. So let's actually apply this third law of planetary motion, and let's use an example here. So let's say we have two planets that are orbiting a star, Gliese 876, and that's like one of the first stars where we actually discovered planets outside of our own solar system. And the semi-major axis of each of these planets' orbits is given in what are called astronomical units. And an astronomical unit is defined as the average distance from the sun to the Earth. So Earth has an average distance of 1 astronomical unit from the sun. And then we measure the distance from we measure the distance of other planets relative to the sun in terms of these astronomical units. And then we need to actually write an expression for the orbital period of this planet C. So we're actually given a variable for the orbital period of planet B, and we have to come up with an expression for the orbital period of planet C. Okay, so let's write down Kepler's third law of planetary motion, which says that the square of the periods is proportional to the cube of the semi-major axis, or the average radius. And let's go ahead and start plugging in some values here. So for the period of planet B, that's going to equal little t. And then this distance, the semi-major axis of this planet, that's going to be 0.13, and then this one, planet C, is going to be 0.208. So when I plug everything in, it's going to look something like this. Okay. And since I've obviously run out of room, let me actually transfer that to another slide here where we have plenty of room to work. So here we go. It's the same thing that I just wrote down on the previous slide. And then now let's go ahead and evaluate what's inside here. So if I take 0.130 divided by 0.208, I get 0.625, and then I have to cube that. When I take the cube of that, I get 0.244. Okay, so now this is equal to 0.244. So if I want to get, if I want to undo this square, I got to take square root. So t over tc is equal to square root of 0.244. And if I take the square root of that number, I get 0.494. And so I get t over tc. Oops. T over tc is equal to 0.494. So if I do a little mathematical swapperoo here, I'm going to end up with t divided by 0.494 is equal to the orbital period of planet C. What's 1 divided by 0.494? Well, it turns out to be 2.02. So the orbital period of planet C is a little bit more than twice that of planet B. So it's going to take planet C about twice as long to go once around its orbit than it will for planet B. And that's a way to apply Kepler's laws of planetary motion. And we're going to get an opportunity to do this in class tomorrow, and I look forward to seeing you then. Bye.